So today's lesson is all about radicals. This is going to be a little bit of a complicated lesson just because there's so many parts to this. So you may want to watch this video more than once. So the first time I'm posting it, I'm going to have you watch it on Edpuzzle so that I know that you've seen it. But after that, if you want to go rewatch it on YouTube, then you can skip ahead and you can get to the parts you want. You can play it at like 2 times speed and whatnot. So the first thing we're going to do is we're going to talk about what is a radical. So you might have seen the word radical before. And so a radical is basically a symbol in math where, if we have, say, the nth root of x, right, this n with the root here, that symbol would be a radical. And so what the radical is telling us is that it's going to give us the number that can multiply by itself n times to give x. And that definition's a little bit confusing, but we'll go over it a little bit more clearly. So n's just any number. N could be 2, 3, 4. So what we're really used to is we're used to something like maybe square root of 9. Right, now notice there's no n there. But this is because mathematicians are lazy. Okay, the square root of 9 is actually the square root of 9 like that with a 2 there. But the problem is square root is so common and mathematicians are super, super lazy that they don't write that little 2 in. It's kind of like 1x, right? Normally we just write x, but really what is x? It's 1x. It's just that this is generally not written. Okay, same thing with the little 2. If it's a 2, it's not written. Any other number is going to be written, but a 2 is not written. So basically, anytime you have a radical, without the number here, that number is a 2. So basically, this 2 is saying what number multiplied by itself would give us 9, right? And we could try 2 times 2 is 4, it doesn't work. 3 times 3 is 9, that does work. So the square root of 9, the answer results in 3. Why? Because 3 times 3 equals 9, and that's the definition of our radical. Now, we don't just have to have the square root, though, or, with one with the power of 2. We could have a radical with a 3 there, and we call this a cube root. So, for example, we could have a cube root of 8. And so this is saying what number times itself 3 times gives 8, right? If we tried 2 times 2 times 2, 2 times 2 is 4, 4 times 2 is 8, right? So that means that this 2 multiplied by itself 3 times gives 8. Right? We could have lots of these. We could have the cube root of 64, and you might not know this one, but that's also why we have this handy sheet here, right? So we can kind of go here and try to find 64. And that is a 3, 4 to the third power. So it's kind of going backwards for powers, right? Radicals are kind of undoing exponents, right? So they're the inverse of an exponent. Just like adding and subtracting are inverses, right? If I do x plus 3 and I do x minus 3, those are the opposites. Well, an exponent is the opposite of a radical. If I do x cubed and I do the cube root of x, those would cancel out. So anyways, going back to this was 4. As we saw in the table, 4 to the third power was 64. Right? So if I know 4 to the third power is 64, then I also know that the cube root of 64 goes back to 4, right? I said they're inverses, that they undo each other. Right? This also means that 4 times 4 times 4 gives us 64. Right? So you don't have to write any of this stuff over here on an exam. You could just look at this chart. I'm going to let you use this chart on the test. So you just look at the chart, find, okay, 4 to the third is 64. So the cube root of 64 would be 4. So that's kind of how that works. Now, there's one more little kind of complicated thing. Actually, before I go there, though, just when we're talking about these, right, if I had, for example, we say that's the square root of x, right? So even though there's not a 2 there, we have to remember it is a 2. So it's the square root of x. This would be we call this the cube root of x. So when we're talking about radicals, another word for them would be a root. So the cube root of x, and so on. This would be, once we get to 4, we just call it the 4th root of x. Right? 4th root, 5th root, and so on. So if I had, for example, like, let's say 9 square root of x, we would just call this the 9th root of x. So square and cube, we call that. But then after that, we just call it 4th, 5th, 6th, 7th, and so on. All right, so that's kind of the naming of them. So one more complicated thing I want to point out with this is our negatives. Okay? And I want to kind of think of this starting off with exponents. Okay, because remember, we said that radicals are undoing the inverse. They're the inverse of an exponent. So if I had negative 2 squared, that's going to be negative 2 times negative 2. Well, what's a negative times a negative? That's a positive. And if I have positive 2 squared, that's 2 times 2, which is, again, positive 4. So this gets a little bit tricky, because if I have the square root of 4, most of us are so used to, from 8th grade or from middle school, saying that the square root of 4 is just 2. But it's not only 2. It could have 2 possible different answers. Right? So the square root of 4 can actually be 2 or negative 2. And that's the answer you need to give me, is either one. We're not sure if it's 2 or if it's negative 2. It could be either one, right? Because negative 2 times negative 2 gives us 4. Sometimes in math, you'll also see this written as plus or minus 2. Because again, mathematicians are lazy. They like to write less. So this here, these kind of mean the same thing. So you can write it either way. But what about with a cube root? Or, a cube. So if I have negative 2 cubed, that's negative 2 times negative 2 times negative 2. Well, the negative 2 times negative 2, this part is 4, positive 4. Positive 4 times negative 2, 4 times negative 2 is negative 8. And then if I have positive 2 cubed, well, that's just 2 times 2 is 4, times another 2 is 8. It's always positive. So when I do these guys, we don't get that issue. So if I had the cube root of 8, I get 2. But if I had the cube root of negative 8, I get negative 2. There's no or. And we're going to talk about the pattern and how to know when it's the or and when it's not. But before I do that, I want to come back up here to this guy and think, what would be the square root of negative 4? So is there a number out there where if I multiply it by itself, it gives me negative 4? And the answer is actually no. There's no such number, right? Because if I'm only multiplying anything by itself, well, if I have a negative, if it's by itself, I have to have another negative. What's a negative times a negative? It's a positive, right? So some negative number times some other negative number. Those can almost look like angry faces or something. So any negative number times another negative number, it's going to result in a positive number. So there's no number in the world that I can multiply by itself to give me negative 4. So this is actually undefined, or we can say DNE does not exist. So, but here with the cube roots I could. And the reason why is when I have my first negative number times my first negative number, this part turns positive. And then when I multiply it by the third time, well, now a positive times a negative, that answer is negative. And so what this has to do with is it has to do with evens and odds. So what's going to happen is that with, and we can just kind of write this down, with even roots, okay, our square root, like if we have the square root of, say, 9, we get 2 answers. We get positive 3 or negative 3. Okay, so that's kind of how that works. And if I had the square root of negative 9, we get undefined or does not exist. So kind of what we can say is that with even roots, the inside must be positive. And our answer will be, our positive, write that a little bit better, will be our positive solution, or our negative solution. So we have to include both. Okay, you have to write both, positive 3 or negative 3. Okay, but with odd roots, this doesn't happen. Right, with odd roots, I'll choose 3 again. The cube root of 27 is just positive 3. And the cube root of negative 27 is just negative 3. And so here, our inside with an odd root, the inside can be positive or negative. And our answer will have the same sign. So if our inside was positive, our answer is positive. If our inside was negative, our answer is negative. So kind of moving on, and let's just do 2 examples just to really make sure that we have this. Okay, or a few. Let's just do a few. So if I had, for example, the square root of, let's say 81, then let's do a few more. Let's do like 3 or 4 at a time. So we'll add in the cube root of 512 and the fifth root of negative 1024. And if you need to use, and we can even, let's do one more. Let's add in like a 6th root. Let's do something a little tricky. So actually, I added in 2 more. We added in 6th root of 64 and 4th root of negative 625. So we have all these. Let's just kind of think about them. Square root, there's a 2 here. So what number to the second power gives 81? You should know this in your head, 9 times 9. But if you don't, just look for something with the second power giving 81. So I'm just kind of going across the second row, and we see 9 is there. So our answer will be 9. Now, we need to be careful though. It was even, so our answer is actually 9 or negative 9. Now, cube root, this is an odd, so we're only going to have one answer. It's only going to be the positive answer. So now we want a number where to the third power gives 512. So we're going to do that same thing. We're going to be looking on this third power row. We're looking on this third power row, and 8 to the third power gives 512. So our answer is 8. So positive 8, because it was an odd power, we only include the positive case. Now we have another odd power, so negative is okay, and our answer will be negative. So something to the 5th power should give 1024. So we're looking in the 5th row. 4 to the 5th gives 1024, but it's going to be negative 4, right? And you can check your work. You can do negative 4 times negative 4 times negative 4 times negative 4 times negative 4 on a calculator, and you'll end up with negative 1024. All right, and then next one, 6th root of 64. So we want something to the 6th power, giving 64. So 6th power, it's this first one, it's 2. But again, the 6th power is even, so whenever we have even, we're going to say 2 or negative 2, right? Because 2 times 2 times 2 times 2 times 2 times 2 will give 64. Negative 2 times 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 negative 2 will also give 64. So either one of these can be answers. And then this last one's a little bit tricky. Some students are going to get this question wrong. They're going to look on the table in the 4th root place. They're going to see 5, and they're going to put an answer of negative 5. Negative 5 is wrong here. Okay, negative 5 is totally wrong here. And the reason why is if I do negative 5 times negative 5 times negative 5 times negative 5, if you check this on a calculator, you're going to get positive 625. But this asks for negative 625. And remember, with the evens, the inside cannot be negative. With the evens, if the inside is ever negative, your answer is undefined. It does not exist. There is no answer that will work. Until you get to math 3, and then we'll have imaginary numbers, but we're not there yet. So for right now, we're just undefined. So kind of moving on, that was actually just the first part of this lesson. So we're going to have a few more parts of this lesson. So the next part of this lesson is going to be, and you could even draw a line through this, is going to be what we're going to call rational exponents. And so far we've been in radical form. So the square root of x and the cube root of x, these are in radical form. Now, what power would x have? It's x to the first power. This is x to the first power. We can actually change these into what we call rational form. In rational form, the square root of x is going to be defined as x to the 1/2 power. And the cube root of x would be x to the 1/3 power. These are the same. It's written the same. It's just a different way to write it. So this is going to be our rational form, and we call this just kind of like a rational exponent. And so it's kind of like, remember how when we had negative exponents, like x to the negative second, that's the same as 1 over x squared. We're just writing it a different way. This is the same thing. Instead of writing it with a radical, we can write it as a fraction. And that can help us out with some of those exponent rules, right? Like the adding rule or the distributing rule. If we have a fraction, then we can actually do math, right? We can add it up. Whereas if we have it in radical form, we can't really add right now. So that's why sometimes this method will be preferred, especially in higher math classes. For this class, we're not going to worry about it too much. We're just going to practice kind of writing it back and forth. So that's really going to be the gist of what we're doing, is we're just going to worry about writing it back and forth. So it's not always going to be a 1 inside, though. We want to be careful. So we could have something like, say, the square root of x cubed. And so remember, what number goes here? There's a number that goes here. It's a 2. And so if we look, where did this 1 come from in the 1/2? That 1 came from where the x was. Where did the 2 come from? The 2 came from that spot. So it's going to be the same thing here. I'm going to have x, and then to the 3 over 2, right? This 2 is going to come over here. So kind of the rule that you could kind of think of is that if I have b square root of x to the a power, then this is x to the a over b. And so I always think, b's first, a's second. That doesn't really make sense. So I kind of just think that my answer is going to be like, if I have a box, square root of x to another box, right? How do I know which number goes on top? It's x to the inside over outside. So I was just kind of remember that. The inside over the outside. Okay. So that's kind of the general rule for converting them. And you can convert it either way. And our homework's going to ask us to do both. So they might say, write as rational form or as a rational exponent. Right, so there could be an example. And maybe they give us, the cube root of 15. And then maybe they also give us, say, the cube root of y to the 7th. Maybe they do an easy one. They just say, hey, square root of x. So cube root of 15, that's 15 to the first power. There's no number there. So this is going to be the inside power is 1. The outside power is 3. That's the answer. Here, y, the inside power is 7. The outside power is 3. And here, they didn't, just square root, okay? They didn't write either one, but the inside power is 1. The outside power, if there's nothing there, is a 2. So this will just be x to the 1/2. Right, and we can do that the other way as well. So they might instead say, write each in radical form. And so they might have us work backwards. And we can do that as well, just kind of remembering that the top is the inside, the bottom is the outside. So maybe they give us a few here, maybe they give us 15 to the 1/4, maybe 8 to the 3/4, x to the 2/7, and we'll squeeze in one more, z to the 9/4. So 15 to the 1/4. Remember, the 1 is inside, the 4 is outside. So the 4 is outside, and then 15 to the 1. We don't write to the 1, so we're just going to write it the 4th root of 15. Here, okay, the 3 is inside, the 4 is outside. So I always kind of start with the bottom because that's outside. Okay, of 8 to the 3rd power. Here, outside is 7. So 7, and then x squared. And finally, the outside is the 4. So 4th root of z to the 9th. The 9 is inside. Okay, so again, all I was doing each time was taking the top number, putting it on the inside with my base, and then the bottom number goes to the outside. All right, so that was part 2. There are 3 parts to this lesson. So again, if you want to put one more line, this is the 3rd part. And this 3rd part is about simplifying radicals. I think Michael had asked about this. We had an extra credit question on it. Now we're going to actually learn it. So simplifying radicals. So we have 3 parts to this lesson. I know it's kind of tricky. So that's why I recommended at the beginning that you may want to kind of pause this video at times or go back and rewatch it on YouTube so you can skip ahead. But basically the concept of simplifying radicals is sometimes we have a number like the square root of 10. Okay? Now, the square root of 10 is not on our list, right? We cannot find anything on here with a 10. But, I know 3 squared is 9, 4 squared is 16, right? And this is a square root. That's why I chose the second row. So I know my answer is going to be something in between 9 and 16, right? I don't know what it is, but square root of 10 does have an answer. And so actually, if we use a calculator and we do the square root of 10, actually this one goes backwards, we get 3.16. And that makes sense. 3.16, I'll say 23. It's up to 4 decimals. That makes sense because, right, we said square root of 9 is 3, square root of 16 is 4, so it's in between 3 and 4, and it's closer to 3, right, like 3.1, because 10 is closer to 9. So that makes sense. But a lot of times we don't want to actually write the decimal. So a lot of times when we're simplifying radicals, we're actually not going to write the decimal. We're just going to leave it as a radical. Okay, so we would just leave the square root of 10 is just going to stay as the square root of 10. But what happens is, how did we define square roots, right? Like the square root of 9 was essentially, if we wrote 9, if we kind of did a factoring tree, it's 3 times 3. So this is the same as having the square root of 3 times the square root of 3. And I have a pair of them, so I can take my pair of them out, and it just becomes a 3. This works for cube roots too, right? If I had the cube root of 8, well, 8 is 2 times 4, and that's 2 times 2. So the cube root of 8 would be the cube root of, I can kind of write that prime factorization, 2 times 2 times 2. Now, because it's a cube root, instead of looking for a pair of them, I need to find 3 of them. And I can take all 3 of them out because it was a cube root. I'm taking 3 out, and the answer is 2. So that's for numbers that were on our chart, right? Any numbers on our chart, that should work for. But sometimes we have numbers that are not on our chart. So we might have something like, say, the square root of 20. In the square root of 20, we're going to do the same process. We're going to make a factoring tree. This is 2 and 10. And then from 10, we can go to 2 and 5. Right? So we're just making this factoring, prime factoring. Okay. And so now we have the square root of 2 times 5. Now, I do have a pair of 2's, and we can take this out to the outside. Now, before, it was the only thing. But now, remember, when we took our pair of 3's out, it was just 1 3. When we take our pair of 2's out, it's just 1 2. It's not 2 times 2, it's just 1 2. Right? Because the square root of 2 times 2 is just 2. Right? It's that number times itself. So we're just going to write it once. But we still have the inside, which will be the square root of 5. So the 2 came out, but then our square root of 5, that stayed inside the radical. And so that's kind of how this works. That's how this concept of simplifying a radical works. Is that we're going to do a prime factoring tree. We're going to take out any pairs that we get. And then the inside will basically stay, what it is. So we could do a couple, more complicated, a little bit more tricky examples with this. So for example, maybe we would do something like the square root of 80 or the square root of 45, something like that. Let's try 45 first. So the square root of 45, right? We're going to do our prime factoring tree. We have 45, and we want to think, what two numbers could I multiply 45 by? I'm thinking of 5 and 9. That's what popped into my head. Then 9, I could think of 3 and 3. So these numbers here, I'm going to write inside my square root. I'm going to write the square root of 5 times 3 times 3. Now, do I have any pairs? Yes, I do. I have a pair of 3s. So I can take that pair of 3s outside, and we get 3. Inside is still a square root of 5. Now, be careful how you write this. It's not the cube root of 5. That's wrong. It's 3 times the square root of 5. So it's kind of like 3 times the square root of 5. Okay. So that's our answer. 3 times the square root of 5. 2 times the square root of 5. Right? We could do maybe 2 more hard ones, and then we'll be done for the day. So we have 80. And 80, I could think of maybe 10 and 8. Then 10, maybe I think of 2 and 5. 8, I think of 2 and 4. And then 4, I think of 2 and 2. So this square root of 80, when I write out that prime factoring, it's the bottom row. 2 times 5 times 2 times 2 times 2, that bottom row. So 2 times 5 times 2 times 2 times 2. And I like to just kind of rewrite this. It's easier for me when I rewrite it when I have my pairs next to each other. So 5 times 2 times 2 times 2 times 2. Now I'm just going to circle a pair, and there's a second pair. So they can come out. So this gives me 2 times 2, and then inside is still square root of 5. Now I do multiply those. That's going to become 4 square root of 5. Right? So notice that each time I took out a pair, I took out this pair, and I wrote a 2. Then I took out the second pair, I wrote times 2. It's not 22, 2 times 2. 2 times 2 is 4. It's also multiplying, not adding. I know 2 plus 2 is 4, but we're multiplying here. Okay, and we'll see this, and we'll do one last example. So do kind of a little bit of a trickier example, which would be, let's do the square root of 40 times the square root of 18. Now, they're both square roots. So, one thing I could do is I could do 40 times 18 because they are like terms. They're both square roots. I could write this as the square root of 720. This would work. But I actually don't want to do that, even though it works, because if I had to do a factoring tree for 720, it's way bigger than just doing a factoring tree for 40 and for 18. So that's what I'm going to do. I'm going to do a factoring tree for 40, and that's 4 and 10. This is 2 and 2, and this is 2 and 5. And then I'm going to do a factoring tree for 18, and this is 3 and 6, and this is 2 and 3. And so now I can basically take both of these, and I can write them all under one kind of radical. So 2 times 2 times 2 times 5 times 3 times 2 times 3. Right, and then again, I'm going to rewrite them just so I like to, sometimes I'll just write all the smallest numbers first. So I have 1, 2, 3, 4 2s. Then I have 2 3s. And then I have that 5. So I have a pair of 2s, another pair of 2s, and a pair of 3s. And so I get 2 times 2 times 3 outside, and then inside is still the square root of 5. 2 times 2 is 4. 4 times 3 is 12. So our answer would be 12 square root of 5. And that's kind of how that works. I think, let me double check something. Okay, yeah, that was perfect. So sometimes you'll have more than one number like inside. So like if I had like something like this, like 2 times 2 times 2 times 3 times 5, right? If we got this as our factoring, I only have one pair of 2s. I don't take this other 2 out. So this would simplify to 2. And then inside, I have 2 times 3 times 5. 2 times 3 is 6. 6 times 5 is 30. So this would be 2 squared of 30. So that can happen as well. So just kind of watch out for that. So our homework is going to be all this stuff. So basically for our homework, we are going to have the skills page. We'll also have a Mathia, but we'll have the skills page, and it's going to be the entire section 4. So just the entire section 4. So part A is super easy. I'll just do an odd answer from each of these. Part A, we're just simplifying. Find the bigger term. It's the 9th. So cross out this, put a 1 there, minus 4. This is 1 over x to the 5th. Just remember with the to the 0 power is 1. Okay. Then evaluate each expression. This one's really easy. I'll do number 4 and 8, so I do 1 odd and 1 even. So cube root of negative 343. We're going to go on the cube root side, find 343. That's 7. Okay, so this is negative 7 because 7 to the third power is 343 and then negative. Then for the 8, we have 625. Number 8, we have 4th root of 625. So we're going to be looking on the 4th term. For 625, we get 5. But we need to make sure that we answer 5 or negative 5. Both answers because it was an even. Okay, then over here, write each radical using a rational exponent. So we're going to use that kind of rule where we're going to have, this converts to x to the inside over the outside. So if I did, 2 and 4, this is 5 to the first power. So 5 to the first power over the third power. Same thing, x to the first power over the third power. Nice and easy. This one's going backwards. So we're just writing it back into radical form. So my bottom power goes outside. My top power goes inside. I don't really write the 7 to the first. If it's to the first, we don't really write it. If I did something like number 8, the 5th goes outside, and then we have 8 squared. And like say number 12, the 2 goes outside. If it's a 2, I don't write it. If you write it, I'm not going to mark you down, but we don't really write the 2. It's just a square root. And m to the 5th. All right, so that's how those work. E is the same thing. It's just that they made it a little harder. It's really not that much harder. Right, the bottom term is, the outside term is the bottom. The inside term is the top. So this would be 4/5. Right, and if we have a square root, there's an imaginary 2 there. So this would be the inside term goes on top. The outside term goes on bottom. So you can do the rest. And then these last ones are rewriting. We just did some of these. I think we literally did square root of 40 as an example. I'll do number 4. So on number 4, I'm going to write 12. That's 2 and 6, and 2 and 3. And we'll have 8. That's 2 and 4, and that's 2 and 2. So I'm going to write square root, and we'll just kind of include all of these guys. So 2 times 2 times 3 times 2 times 2 times 2. And if you want to do it right here in circle pairs, you can. I like to just write all my 2's first. 1, 2, 3, 4, 5 of them. And then I have 1, 3. So I have a pair, and I have a pair. Each pair is going to come outside. So this comes out 1, 2 times the second 2. And then inside is 2 times 3. So this becomes 4 outside and 6 inside. So 4 squared is 6. So that's our homework. Should be easy. And then, just get at it. So this is due Sunday. So you'll have until Sunday to do it. I know it's a lot of questions, but we have all the way until Sunday. All right, if you have any questions, shoot me an email. I know this was a long lesson, but there was a lot to go over. And you may need to go back and kind of rewatch some of it as you work, or you may be fine with this. All right, have a good weekend, and I will see everyone on Monday.